Today we are going to start with the topic potential energy in an external electric field. So under this topic we are going to calculate the potential energy in a presence of an external electric field E. So in this we have three different cases. The first case where we are going to find the potential energy for a single charge. So, suppose we already have an external electric field E, which is in this direction, and the external electric field strength is E. And this electric field definitely will have certain potential associated with it, which is V. Now, for this electric field at a particular point, I choose P, and the potential of this point in this electric field, let us suppose this is V. Now I am trying to bring a charge Q from infinity to this particular external electric field. To bring this charge to this external electric field at a point P, the system must do some work against this external electric field. And this work that is done by this charge, or the system of charge, here we are talking about single charge. So this charge, to bring it from infinity to a particular point in the external electric field, it must do certain work. And this work we already know would be Q into V, that is Q into the potential of that point. This work is what is going to be stored in this particular point. And this work is again the calculation of the potential energy of this charge at this particular point. So we can say that the potential energy due to the single charge in an external electric field E at a point P which has a potential V is nothing but, the work done is nothing but Q into V. Because this work done by the charge is stored as the potential energy, which is denoted by U. Now let's see what is the unit of this potential energy. As we already know, that suppose if I take Q is equal to 1 electron, and the charge of 1 electron, which we already know, is 1.6 into 10 power minus 19 coulomb. And suppose the volt or the potential, I take it as 1 volt. Then therefore, according to this formula, the potential energy will be nothing but Q into V, which is 1 electron into 1 volt, which I can write it as 1 electron volt. This is one unit, a particular unit, or it's a SI unit for the potential energy. Now if I just substitute it, this gives me 1.6 into 10 power minus 19 coulomb into 1 volt, and coulomb into volt, this gives me another very well known unit, that is called joule. So from here we know that the potential energy has got two, specifically when we are talking about potential energy of a single charge, it has got two different units. One is the electron volt, another unit is the joule. So from here you can very easily understand the relation between electron volt and joule, which is 1 EV is 1.6 into 10 power minus 19 joule. So this is what, when we are talking about the unit of potential energy, right? But the potential energy of the single charge is given by Q, the amount of charge, and the potential at that point V. Now when we are talking talking about potential energy of two charges. Now as we are talking about potential energy of two charges, what I see, the same situation where I have an external field E, and let's take there are 2 points in this field P1 and P2 which are at a distance R between them. In the point P1 I already must have had one charge Q1, because now I am talking about two charges. So first charge is Q1 which I have brought from infinity. So work done W1 to bring this charge from infinity to this point P1 which has a potential V1. We know from our previous discussion that W1 will be nothing but Q1 into V1. Now interesting thing, if I am trying to bring the second charge from infinity which is Q2. Now when we are bringing the second charge Q2 from infinity to a point P2, let's suppose this has a potential V2. Now when we are bringing this charge Q2 to a point P2, it is not only working against this external electric field, it is also working against an electric field created by the charge Q1. So when we are bringing a charge Q2 to this electric field or this external electric field, Q2 must be doing two different work. First work it is doing due to the external field, and the second work it is doing due to the charge Q1, or I can say WC, due to the charge. Now this WE which is due to the external field, the work done against the external field, this is very similar to previous one that we have already done. This will be nothing but Q2 into V2 due to the external electric field. But there must be another work that is being done to work against the electric field due to the Q1, and that electric field we all know will be Q1 Q2 by 4 pi epsilon naught R, where R is the distance between these two charges or this 2 point P1 and P2. So as you keep on bringing different number of charges, or if you keep on bringing multiple charges to this external electric field, the charges not only work against the external field, it also have to work against the other electric field that is created by the already pre-existing charges. So here we have talked about the two charges, and therefore what we see, due to the second charge, the potential energy of the second charge due to the second charge will be Q2 V2 plus Q1 Q2 by 4 pi epsilon naught R, right? So in this way you can add on all the potentials or all the potential energies due to the multiple charge. Okay, so now we discuss the last topic in this, that is the potential energy of a dipole. So since we don't have the whole derivation in our syllabus, we are not going to derive the whole thing. So I'll just give you the expression. It is enough to know the expression and to understand how and why it is happening. So suppose I have an external electric field which is E in this particular direction, and I have a dipole placed in this electric field. As we know, dipole means it is two charges of equal but opposite polarity of charge. Let's suppose this dipole have a dipole moment P, and this dipole is oriented, or it is making an angle theta with this electric field. So what we say that the dipole moment of this dipole is in this direction, or the direction of the dipole moment vector, and the vector of electric field, they are making an angle theta. So as we know, if we have to calculate the potential energy of the dipole, then we have to know what is the work done by the dipole against the electric field. And the work done by the dipole is always given as minus P dot E, and here we are talking about dot product of two vectors, and we already know the dot product of two vectors gives us PE cos of theta. It always gives us the cos of the angle between these two vectors. So this is the work done by a dipole against this electric field E, which is PE cos of theta, where theta is the angle between these two vectors, right? And this is the same work which is stored as potential energy. So therefore we can write the potential energy E is nothing but minus PE cos theta or minus P dot E in the vector notation. This minus sign shows us that the work done is stored inside the field, or this is stored inside a field as potential energy. So the potential energy is given as minus P dot E for a dipole with the dipole moment P and the external electric field E. So with this we are covering up all three topics to calculate for the potential energy in the presence of an external field. First thing, we have calculated potential energy for a single charge. Then we have calculated potential energy for two or multiple charges in an external electric field. And lastly, we have known the expression for the potential energy of a dipole placed in an external electric field.